Diptiman Sen. Diptiman is from IISc Physics Department. He is going to talk about Josephson junctions of multiple superconducting wires.
Yeah. Okay, so I'd like to first thank the organizers Urvashi and Dipankar for inviting me to give this talk. So this is some work that we did on Josephson junctions of several, actually 3 superconducting wires which turn out to have some topological properties. So this work was done in collaboration with my ex-student Indrila Deb, who is now a postdoc in University of Basel, Switzerland, and Krishnendu Sengupta in IISc Kolkata. So the plan of the talk is as follows. So I'll give a very brief introduction to topology and topological invariance, which is probably known to, I'm sure known to everyone. And then I'll tell you about our model for Josephson junctions of multiple wires, and then 3 different effects in such systems. The AC Josephson effect, where the topological aspect really comes through very clearly. Sharpedo Plateaus, actually, depending on whether it's a plot of current versus voltage or the other way, it's sometimes called Sharpedo steps, but the way I'm going to show it, it looks like plateaus. And then the fact that the junction can have a non-zero magnetic moment under certain situations. And the work is published in this paper last year. So first, a few words about topology. So as you know, this is a branch of mathematics where we study those properties which do not change if you make some small changes in the system. Okay? And if you can define an integer which remains the same under those small changes, it's called a topological invariant. And since it's an integer, you don't expect it to change under small perturbations unless you do something drastic to the system. So just to give 2 examples of topological invariants. One is you take a point, say the origin and a plane, and draw a closed curve. Then the number of times this closed curve winds around the origin in one particular direction, let's say anti-clockwise, that's called the winding number. Now this is a topological invariant because unless the closed curve happens to go through that origin, if you leave aside those curves, you have a well-defined integer, and it doesn't change if you change the closed curve, deform it in a few places. Okay? So some examples is the closed curve with winding number 1, -1, 1, and so on. Very soon, if it becomes quite difficult to see what the winding number is. So there is of course a mathematical formula for figuring out the winding number given a closed curve, which I'm not showing here. So as I said, the important thing is that except for a special case where the curve happens to go through the origin, the winding number doesn't change under small deformations. So there is a generalization of this to closed surface in 3 dimensions. So this is a little hard to show, but imagine that there is a surface, a sphere which is red. I'm only showing some particular contours on the sphere. And there is another sphere which is in blue. So the number of times the red sphere wraps around the blue sphere is kind of winding number of one sphere around another. So I'm calling this a wrapping number for short. And this is actually related to something which I'll come to call the churn number. And once again, this is a topological invariant. It can only take integer values, and it doesn't change if the spheres are deformed a little bit. So next thing I would like to mention is something called the Berry curvature. So suppose you have a 2-dimensional system. This could be a system of electrons, or it could be a system of spin waves, magnons, and so some 2-dimensional quantum system. Let's assume that it's translation invariant, so that you can use the momentum as a good quantum number. And let's say the Hamiltonian has a number of energy bands. In one particular band n, let's say that En and psi n are the energy and wave function, and they are functions of the momentum kx and ky's because it's 2-dimensional. So given these wave functions, you can define these objects, say I psi dagger del psi by del kx, let's call that ax, and I psi dagger del psi by del ky, call it ay. This n is just the band index, it just goes along. The way it's defined, these turn out to be real objects, and they are of course functions of kx, ky themselves. So these sort of look like some vector potentials. So given two vector potentials in two dimensions, you can define a corresponding kind of magnetic field, which is the curl of that. So define B in this way. It can also be written directly in terms of the wave functions in this way, minus twice the imaginary part of this quantity. So this is called the Berry curvature. Now given the Berry curvature, the next thing you can do is you can define a Chern number, which you get by integrating the Berry curvature over all values of kx and ky. And you need a 1 over 2 pi just to make this an integer. So it turns out that if these wave functions were two component objects, so any two component object you can actually map to a point on a sphere. So you can write a two component object, the upper component has some cosine theta by 2, lower component has sine theta by 2 e to the I phi, and then map it to a point on the sphere labeled by the polar angles theta and phi. So in that case, this Chern number really is the wrapping number of the sphere of kx, ky suitably compactified to the sphere of the wave function. But the systems that we are going to look at, say with three superconducting wires, the wave functions will have three components. So they don't really directly have this interpretation of wrapping of one sphere to another. Nevertheless, you'll see that you can define a Berry curvature and a Chern number, and they prove to be very useful. Okay. All right. So the main point of this talk is that a junction of three or more superconducting wires will typically have Andre bound states. This is true even for two wires. But if you have three or more wires, these Andre bound states, they form bands as functions of the superconducting phases. And these bands will generally have a non-zero Berry curvature, and then you can have effects, physically observable effects due to that Berry curvature. So this was first pointed out in this paper. So this is kind of a very interesting paper which first showed that Josephson junctions are a new kind of topological system, where the role of momentum in usual topological systems is played by the superconducting phases. And then there have been a lot of papers following up on this. There is another paper in 2018 where they showed that if you take four superconducting wires, then as a function of the superconducting phases you can actually get Weil points. Right? These bands may have Dirac points, or they may have conical points touching each other, just like a Weil dispersion in 3 dimensions. So you can have all kinds of interesting effects in these systems which you have, if you already have seen in electronic systems. Yeah. We'll come to that. Yeah. It could be S wave or P wave. Yeah. Okay, so the particular model that I'm going to look at is a junction of 3 wires. So what we have is there's a little region in the middle in orange, which is a normal region, very small, and then there are these superconducting wires, 3 of them. So SC1, SC2, SC3. Eventually, of course, these wires are connected to leads, normal leads, very far away. But we're just concentrating on this part of the entire system. Now this portion in the middle is characterized by a scattering matrix, and this is a normal scattering matrix S. By normal I mean that an electron or a hole which comes along the wire and hits this region can get scattered back only as an electron and as a hole. So we don't assume any Andre reflection from here. But on the other end, when the electron or hole goes to the top, when it gets reflected, it can get reflected as electron hole, or the other way. You can have either normal or Andre reflection from the other side. So that's the model. Now, okay, so as I said, the orange portion here is governed by a normal S matrix. So it has to be unitary. It's going to be a 3 by 3 unitary matrix. Whereas at the end of the superconducting wire, you have Andre reflection. Electrons get reflected to holes and holes to electrons. And that reflection amplitude is proportional to this quantity. So there is this object which is just a pure phase, is the energy of the electron, and delta is the superconducting pairing, and when it gets reflected, it actually gets reflected with a phase, e to the minus I phi or I phi, plus I phi or minus I phi, depending on whether it's electrons to holes or the other way. So this is where the superconducting phase shows up. Now we are actually going to make a simplifying assumption in this model that this delta is the same on all the superconducting, which is not very realistic, but it simplifies a lot of the calculations, and so that's what we are going to do. Now it turns out that some of these Andreev reflection amplitudes have additional factors plus minus 1 depending on the spin of the electron and whether the superconductor has a P wave or S wave, and I'll show you one of those factors a little in the next slide. Okay. So just for mathematical convenience, if you have a system of n wires, let's say you introduce a n by n diagonal matrix, okay, which I'll call e to the I phi. So this is just a matrix whose diagonal entries are given by e to the I phi I. One I goes from 1 to n, okay, for labeling the different wires. And as I said, we'll assume the magnitude of all these pairing amplitudes are the same in all the wires. Then there is this very important equation which was actually first found by Binneker in a very influential paper. That if you know this S matrix, you know this all these different superconducting phases. So these are all n by n matrices. So the eigen states and eigen values of this matrix give you the Andreev bound state energies. So the eigen value of this matrix is, let me call it 1 over a squared, and from that you can figure out what the energy is, and that gives you a bound state energy. Okay. Okay. And so of course this A depends on the superconducting phases. Okay. Now this is actually the equation you get if all the wires have S wave pairing. I've suppressed the spin label, so I'm assuming this is actually for spin up quasi-particles. If you have spin down quasi-particles, there are some minus signs which appear. Also, if some of the wires have P wave pairing, it turns out that for those wires in those diagonal entries of e to the I phi, you put a minus sign. If it's e to the I phi, you don't put a minus sign if it's e to the minus I phi. Okay, so this is all there in the derivation due to Binneker. Okay. So the equation changes a little bit if some of the wires are P wave. Okay, now where does the Berry curvature come in? So if you have n wires, we get n bands of Andreev bound states this way for spin up, and similarly n bands for spin down quasi-particles. So let's label these bands as n comma sigma. So n goes from 1 to the number of wires, and sigma is up or down, plus minus 1. Sorry. Okay, so they just come out of the solutions of this equation. So this is an eigenvalue equation. So they. Oh, where do they live? They live in that junction region. So, well, in this entire region actually. So that's only here. Okay. So I was not clear enough. So if you have an electron coming in here, it can get either reflected back or transmitted to the other one, and that's described by a scattering matrix S. When the electron goes in the opposite direction and is trying to get out of this, it goes and hits the normal lead at some point, and there it can get Andreev reflected back. So the entire system is just this much. Okay. Outside this are the normal leads connecting to these wires. So well, I would say they live everywhere, but you know this region is very small, so essentially they live in the blue regions. Yes. Okay, so that's where these Andreev bound states are. Now, sorry. These are matrices. So e to the I phi is actually matrix which is e to the I phi 1, e to the I phi 2, e to the I phi 3, and they may not commute with this S matrix which sits in the middle, so they don't cancel each other. S is a scattering matrix. Yeah, e to the I phi is a matrix. It's a matrix whose diagonal elements are e to the I phi's. Okay, and the reason they don't cancel out is there's this S sitting in the middle, which is a scattering matrix which may not be a diagonal matrix. Now in each band, so these are some general properties. The energy in wave functions of course depend on the superconducting phases, but they remain invariant if any of the phases is shifted by 2 pi, right? Because you know, if you change the phase, superconducting pairing phase by 2 pi, nothing should happen. Also, if all the phases are shifted by the same amount, then again nothing will change, because that's just a global redefinition of the superconducting phases. Now suppose we vary only 2 of the phases, let's say phi 1, phi 2, and keep all the other phases fixed, then that kind of describes, that gives you a 2-dimensional system in which phi I, phi j play the same roles as the momentum kx and ky. Okay. So if all the bands are gapped, we can define the Berry curvature in terms of those two, phi 1 and phi j. So you define derivatives of the wave function with respect to phi I and phi j, get the Berry connection, then take the curl and get the Berry curvature. Okay, so in this way, even if you have an n wire system, you can just concentrate on two of the phases and use that to define a Berry curvature and a Chern number. Okay, so in a given band, the Berry curvature matrix is given by this. So this is a real antisymmetric matrix.
That they don't have any overlapping energy.
Sorry?
The assumption is that the bands don't have
The bands don't overlap, that's right. Yeah, so they are separated from each other by gaps. Yeah, I'll show you some pictures of that. Okay, so in general, so those properties that I told you, that if you shift all the phases by the same amount, nothing changes, or you shift them by one of them by 2 pi, nothing changes. That from that you can prove that this matrix, so this is an n by n matrix now, okay, I and j, it just depends on these labels I and j. All the rows and all the columns of this matrix must add up to 0. Okay, so therefore, if you have a capital N number of wires, this Berry curvature matrix has only so many independent real parameters. And now you can see that you need at least 3 wires to have a non-zero Berry curvature. So this is, so if you have 2 wires, you don't have a Berry curvature, and none of these effects that I'm going to tell you about show up in 2 wire systems. So you need at least 3 wires. Here's a few facts about the bound state energies. So first of all, they lie within the superconducting gap, minus delta to plus delta. If all the wires are S wave or all of them are P wave superconductors, the energies come in plus minus E pairs, okay, for each value of the spin and momentum. But you can consider a mixed junction in which some wires are S wave and others are P wave, then they don't come in plus minus E pairs, okay. So then you have an interesting situation in that spin up quasi-particles and spin down quasi-particles don't necessarily have the same energies. There's a funny symmetry that the spin up quasi-particle with energy E there'll always be a spin down quasi-particle with energy minus E. But within the same spin, you don't have to have plus minus E pairs. And so if you have these mixed junctions with some S wave and some P wave, you can get a non-zero magnetic moment. So I'll talk about this later. Okay, now the next thing is the choice of S matrix. So this of course is something that has to be experimentally determined. But in our numerical calculations, we decided to look at 2 cases. One was we took something which is completely symmetric between all the 3 wires. So all the reflection amplitudes are the same, all the transmission amplitudes are the same. This actually has a name. This kind of matrix is called the Griffiths matrix. The person who wrote this book on electromagnetism. So it was first discovered in the context of waveguides, scattering inside a waveguide. This is the most symmetric matrix you can have with, and this can be generalized to any number of wires. Physically, it corresponds to having a barrier which has a certain barrier potential. Okay, and so that parameter lambda shows up in this. Yeah, it is. Yeah. The other matrix we took, so this is actually time reversal symmetry. So time reversal symmetry in this context means that the S matrix is symmetric. Then we also took a randomly generated matrix which is asymmetric, so it's not time reversal symmetric. So these are completely random numbers. Okay, and we'll see what difference there is between these two. Okay, so this is the case of the symmetric matrix with some lambda 0.1. The lambda is the parameter which shows up here. And these are the unj bound state bands. So you see there are 2 bands for each phi 1 and phi 2. So what we have done is I've set phi 3 equal to 0. Because the band energies don't change, if you shift all the phi's by the same amount, you can shift one of them to be 0. So phi 3 is 0. So as a function of phi 1, phi 2, you have these 2 bands which have energies plus minus E at every k. The third band happens to lie exactly at plus delta or minus delta. So within this formalism, you cannot distinguish between them. In any case, if it lies at plus delta and minus delta, it's really at the border with the bulk states. So this band actually plays no role at all in the calculations. So essentially, there are only 2 interesting bands. And if you calculate the Berry curvature, you see that they're large only at 2 points. And if you look at the Chern number, it's 0. The integral of this over phi 1, phi 2 is 0. That's a general property. For any symmetric matrix, the Chern number must be, the total Chern number must be 0 in each band. I mean, the integrated Berry curvature, which is the Chern number, must be 0 in each band. On the other hand, if you take this asymmetric matrix, then these are the energy bands. Once again, one of them sits exactly at plus delta and doesn't play any interesting role. The other two, again, they are related to each other by plus minus E. If you calculate the Berry curvature for this band, let's say, you get a single peak and the Chern number is not 0 and it's minus 1. It has to be an integer. Okay, so for asymmetric matrix, the Chern number may be non-zero in some bands. Now we look at the expression for Josephson current. So, so if you apply voltage to Vi to a particular wire I, then we know that the phase in that changes in time according to this equation. So this is one of the important equations for the Josephson effect. Phi dot is 2E by h bar times the voltage there. So in some sense, okay, so then this is the other equation, that the current in I is given by the derivative of the unj bound state divided with respect to the phase in that band, sum over all bands and sum over all spins times this Fermi-Dirac distribution function. And so this is the term which was known earlier. So these two were the two terms that you get for phi dot and current. Okay. So these are well-known equations for Josephson current. So the new thing that was discovered in that first paper that I pointed out by Dewar and all is that you get this piece appearing now, which is proportional to the Berry curvature. So in some sense, you know, this is kind of analogous to what you would get for a particle moving in an electric and magnetic field. So if you think of phi as a coordinate, then the derivative of E by phi is, it's like the electric field. If you think of E as the potential, this is just an analogy. So if you think of E as the potential, gradient of the potential with respect to position is the electric field. And then this is the term which is r dot, the velocity, times some b, and that's the magnetic field. So, you know, this kind of extra term appears in many places. It also appears in condensed matter physics if you look at the evolution of wave packets, momentum and coordinate in the presence of a band with curvature. Okay. So this was shown to appear here also in this problem. So this is a new thing that appears if you have 3 or more wires. Okay, so now suppose, so we're going to look at the AC Josephson effect. So you apply constant voltage. So let's say you apply constant voltage to wire 1 and nothing to wires 2 and 3. Then the phase in wire 1 will change linearly with time according to that equation, whereas phi 2 and phi 3 will be constant. So then when you work out, so let's say you work out phi, you set phi 3 equal to 0 as before, but allow phi 2 to be a free variable and see what happens when for different values of phi 2. So phi 2 is a constant, phi 1 changes like this. So you discover that there is no current in wire, there is no average current in the wire where you are applying the potential. So I should explain here that all the currents in all the wires will now oscillate in time. So we are just going to look at the time average current, the DC part. Okay, so the interesting thing is that you are applying a voltage to wire 1, but the average current there is 0. But there is an average current in the other 2 wires, which of course have to be opposite each other because of total current conservation. And they are given by this expression. So you see right away that the Berry curvature shows up here. In fact, the other term, which is gradient of E with respect to the superconducting phases, cancel out. You only get a contribution from the Berry curvature. So you have this thing called a transconductance. So you apply a potential to wire 1 and you have a current in wire 2 in a different wire, and that's non-zero given by the Berry curvature. And if you integrate that over phi 2, you get this 4e squared by h times the Chern number. So this object in principle tells you what the Chern number is, if you can measure this object, transconductance, but you have to integrate it over the phase of the one of the wires. Okay, so here's some pictures of this. So I'm plotting the current as in wire, I think it's, actually they're both there. The blue is I2 and black is I3, they're always equal and opposite. So as a function of phi 2 you get this plot. Notice that there are peaks in them which are exactly the places where you have peaks in the Berry curvature in the previous plots that I showed you. And okay, so the peaks in this current coincide with the peaks in the Berry curvature. This is for the case of the symmetric S matrix at the junction. You can do the same picture for the asymmetric S matrix, and then you have a single peak, which is exactly again where the Berry curvature had a peak for that wire.
S matrix
So the previous one is a symmetric one with lambda equal 0.1. It's not, yeah, the second one is random. So this is the asymmetric randomly generated S matrix.
Because then there will be fluctuations with respect to randomness also, right?
Sure. No, but it turns out the Chern number has to be quantized. So even if you vary S randomly, it will have a non-zero Chern number which is fixed to be -1 or +1. Of course, at certain points it can flip, but over a wide range of randomness, the Chern number will be fixed. Yeah, 5 minutes? Okay. So next let me tell you about the Sharpedo Plateaus. So for that, so this has been studied for a long time. So you need an RC circuit. So you have these superconducting wires, but now they are in parallel to a resistance and capacitance, and I'm assuming that R and C are the same for all of them. And you have these voltages and currents. So now the earlier equations for the current, we had these terms, now we have to add these terms. So these are just like Kirchhoff laws, okay, in this circuit. Then what you do is apply a current in wire 1, and it has this constant piece I and an oscillating piece A. And then let's say the voltages in the other two are 0. So this looks a little odd, but this is the way Sharpedo steps are actually defined. You apply a current which is simple, and you try to look at what the potential is in that wire. Okay. So you get this equation, this is non-linear, and you have to solve it numerically, which we did, but you can actually understand what's going on. So what you do is first is you ignore this term and solve the rest of the equation, which is a linear equation. Then you put back this term perturbatively, assuming it's small. This is a legitimate thing to do if the superconducting pairing is very small compared to all the other energies like the Fermi energy. Now this energy is a function of the phases, and so it will have a Fourier transform, Fourier series, because it's a periodic function with period 2 pi. And then you discover that you have, if you look at the time average value of this V1, it will have plateaus as a function of I at rational multiples of omega, m by n, where m is any integer and n is corresponding to this coefficient. So the plateau will have a width proportional to Cn. Now for two-wire junctions, typically E is proportional to cos phi, so you only get n plus or minus 1 components appearing, and that's why you get Sharpedo plateaus at integer multiples of omega. But here, because energy is such a complicated function of phi, you get all the Fourier coefficients appearing in general, so you can actually have plateaus at arbitrary rational multiples of the frequency omega. So in principle you can have this, what is called this devil's staircase of plateaus, infinite number of plateaus. Okay, so there's a picture where plateaus in, so the time average value of V1 versus I, and you see plateaus at integer multiples of h cross omega by 2e, which are these easier to see plateaus. But if you look very closely, there are also plateaus at half odd integer values of omega, 1 here, 1 here, 1 here, and so on. Okay, the final thing is this magnetic moment of mixed junctions. So as I said, if the wires have different kinds of pairings, so let's say 2 p wave on 1 s wave, then the unrelated bound state energies are not identical for spin up and spin down. Okay, so then the junction can have a non-zero magnetic moment. So here's a surface plot. So I've set phi 3 is 0, the S matrix is symmetric, and as a function of phi 1, phi 2, here this very complicated looking plot. You can see that there are large regions where this magnetic moment in units of mu b by 2, Bohr magnet, is plus or minus 1. There are regions, small regions, where it goes to plus minus 2. Now what you can do is that you can apply constant voltage V1 as in the AC Josephson effect, and now phi 1 will vary linearly with time while phi 2 and phi 3 will remain constant. So that's now like taking, you're holding phi 2 fixed, but you're varying phi 1 in linear in time. So that's like taking a cross section of this plot. And so this is what it will look like. So the magnetic moment will just oscillate periodically in time, and apparently it's possible to detect this by the electric field that is radiated near the junction by this oscillating magnetic moment. There's a paper which we have cited where they've done this kind of measurement experimentally in some system. Okay, so the summary is that, so I've shown you that the Josephson junction of 3 superconducting wires is a topological system, where the bound state bands have very curvature in Chern numbers. The system has a transconductance. So applying a constant voltage to one wire produces a current in the other two wires. And if you integrate that transconductance over one of the superconducting phases, you get Chern number multiplied by 4e squared by h. And then you can get Sharpedo plateaus in a plot of time average voltage versus current. when you vary the current in one of the wires periodically in time. And what is interesting is that the plateaus can occur at any rational multiple of the driving frequency. And finally, for a mixed junction, the junction can have a non-zero magnetic moment, and this will actually vary in time when you apply constant voltage to one of the wires. Okay, so I'll stop there. Thank you.
Thank you, Diptiman. Exactly. One small question.
Yeah.
This magnetic dipole radiation, what is the typical frequency of it?
That will depend on how this phase is varying. Okay, so let's go back to that. So I've assumed some arbitrary time dependence, but basically, the frequency is easy. So when you apply voltage V1, the phi 1 varies with a frequency which is twice EV divided by the Planck's constant.
So it's experimentally it's microwave.
Yeah. So numbers. Okay. I can't really. I mean, it depends on what voltage you apply. You can control it as you like.
No, you asked a question. Typical.
Typical. Okay. I don't know.
Yes. No, after.
So what is the space in which the phis live? So topologically, so it starts out as 3 circles, so that's a torus, T3.
Right.
However, I guess there's an overall translation symmetry, so that takes away a circle. So in the end, is the space a 2 torus?
It's a 2 torus.
It's
yes.
a 2 torus,
Yes.
and you're computing or you're observing the Chern number of a certain U1 bundle over that 2 torus. Is that the right statement?
I'm not sure it's the U1 bundle. So the base space is of course a torus,
Yes.
but the fiber, I guess, is the wave function psi, and that's not.
Yeah, but for a given value, isn't it true that for a given value of phi, but for a given point in the base space, there's just a one-dimensional space. There's no degeneracy in the.
There's no
energy level.
degeneracy.
So then it is.
But-
just,
but
it's just a U1 bundle. Then.
But it's an n
only-
component.
It's an n component, but only the phase is free. Because it's a non-degenerate.
No, but I think all the components of the wave function matter when you're calculating the Chern number. It's not just the phase. It's a Chern number. So I think you really need full information. In fact, I don't believe there's a way of getting just the phase, the wave function in an unambiguous way. It's not a winding number.
It's not a well-defined and ambiguous phase, but the set of possible Hilbert space vectors that represent the state living above a base point is a U1.
Okay.
Right? It can only vary by a phase. So I think it is, well, we can talk later, but I'm
Okay.
pretty sure it is a U1 bundle. Otherwise, you wouldn't talk of the Chern number.
Okay.
You said that if all the 3 wires are S-wave, then you need.
Sorry, if all the 3 wires are S-wave shape.
Yeah.
Okay.
So then you need S matrix to be time reversal symmetry broken, or to have.
No. What kind of superconducting the wires are is a different question from what the S matrix is.
No,
So
so
these are different questions. So the S matrix you can choose in different ways. We chose just to get 2 representative samples, one symmetric, one anti-symmetric.
So if you.
So that's but in addition to that, you can choose the wires to be S wave, P wave, or some mixture.
No, that I understand, but I am saying that if you have all S wave
Right.
and S matrix at symmetric, so in that case, will you have Chern number non-zero or
The total Chern number is 0.
zero? Right?
Yes.
So you need asymmetric to make it non-zero.
Yes. But even if the total Chern number is 0, you still get interesting effects.
Okay.
Right? You saw that you get these.
Curvature is not 0.
The curvature is not 0.
Okay.
So depending on so when you're doing this AC Josephson effect, some of the superconducting phases are varying with time.
Mm-hmm.
If you happen to, while they're varying with time, if you happen to go through a region where the Berry curvature is very large, then you'll see some effect from that. Okay, you don't have to go through both the points of positive and negative Berry curvature in a given experiment. You can.
But you will not call it topological. That's what I was trying to say. That
Because it
Chern
is
number
because it depends on the Berry curvature. So in that sense, some topological aspect is coming in.
Just a brief question.
Yeah.
If you have P-wave wire